So the title of my talk here is Planet Formation by Gravitational Instability around the FUor object V960 Mon. But if I had to choose a bit more of a catchy title, I would probably go with Hollywood, and I'd say Everything Everywhere All at Once. And I think in a few minutes you will notice why I would choose this title. There's no need for a major introduction because we heard a lot about gravitational instability, outbursts, of course. But I want to put the talk in a bit of the context of this conference. So we're talking here about how do accretion bursts influence planet formation, and also how does planet formation influence accretion bursts. And the major problem we're facing as a community in this conference is that we're talking about many different scales. So we go from the accretion onto a protostar to a disk around the star, and finally we've already talked a lot about the influence of the environment, of inflow. Here we see again a dispatch simulation by Christian Kranz-de-Holm from Copenhagen. And yeah, so we have to kind of capture all these effects in our understanding. Okay, I don't know why it broke down, but... Okay, so yesterday we talked a lot about what triggers the FUor event, and I put down here a few of references and scenarios that we mentioned. We talked about GI clumps falling onto the star, giant planet disruption talked about by Sergei, stellar flyby. We're going to hear more about this by Nico probably. And also the classical scenario by Phil Armitage of gravitational instability and MRI in the inner system. And as you can see, many of those scenarios, or like the GI scenarios and also giant planet disruption, like it basically also kind of implies gravitational instability, or at least gravitational instability is of course one of the pathways to form giant planets in the first place. So it's natural that people started to think that these FUor objects might be really good places to look for the signatures of gravitational instability. And when ALMA came up, that's what people did, went there. Okay. Doesn't want to. Let's try here. People like Sarah and Sue in 2012 already said, okay, let's simulate this and let's see how this should appear in ALMA. Fragmenting disk simulation on the left-hand side. On the right-hand side, we can see the predicted ALMA image. And what we can see is that it should produce some observable signatures in the ALMA image. Then other people came, like observers, and said, let's try to observe this and observe these FUor disks. And surprisingly, there are some effects, like Ciesa et al., they found like the shift of the ice line, which is super impressive. But on the other hand, these disks are super smooth in their structure, so no fragmentation at all, which is kind of surprising. It's even more surprising if we then compare this to the near-infrared view of this system, which is super disrupted. It shows a really dynamic environment. We can see here four disks that was published this year by Alice, and we see a lot of structure, a lot of dynamic events, and large-scale effects. And just to put this a bit into context, we can look at the most prominent case, FUor. We see here on the left the sphere image, on the right the ALMA image, and that's just the direct comparison of the two, where we see the smooth millimeter emission and the really disrupted near-infrared view. In the near-infrared, what's really outstanding a bit are these arc-like shapes on the large scale that one of the questions is whether they are outflows that are somehow connected to the FUor events, maybe the present one or maybe one that has happened in the past. Okay, so now I want to focus on a single case, V960 Mon, and just do like an individual case study. I told you before that we have to look at different scales normally, and different scales are relevant in our understanding. And in this case study, we have the benefit that we have the observational data of different scales. And we can start out around a star, so the classical thing, monitoring. It is an FUor star because it has an outburst, of course. And this outburst happened in in 2014, so it was possible to register this outburst and trace the decay afterwards. And that's the light curve we see. And then the good thing is that in 2014, ALMA and FUor, like the most important ground-based telescopes we use to study these environments with imaging of the disk, they were already online. So 2 years later, it was already possible to take images of this FUor object. And if we look at a sphere view, we've seen this a few times in this conference already, we see a really interesting environment. So first of all, I want to point out the scale that we see here. We can see that this image shows about 2000 AU around the primary, which is a huge environment. And I think if this were at a position of FE Orionis, we'd probably see like the inner arcsec of this image just by the limitations that we have from the sphere detector. So here we see this huge environment because the object V960 Mon is at a distance of about 2 kiloparsec. We can see several spiral arms in the north and in the south, and we see a companion around the outbursting star. And when we saw this image with the spirals, of course, one of the first ideas with the history of FUor objects is that one thinks of gravitational instability, that this might be another beacon of gravitational instability at place in the system. And then we wanted to know more what happens in the millimeter emission, because as I told you before, gravitational instability, we would like to see, or we would expect to see some fragmentation or something in millimeter emission. And we took a look at the ALMA data that was there, and we found that, like this is some work done by James and Antonio and Miguel Cargamo, we found that there is a spiral in this system that is kind of in the same location as the spirals that we can see in the scattered light. And it is not a smooth spiral, but we see several fragments. And to make sure that this is a real signal, we try to reproduce this image with several different techniques. So on the left too, you can see T-clean, which is a standard method to reduce ALMA data. Then we also used an independent method that is a maximized entropy method that was done by Miguel Cargamo, where we can see qualitatively the same structure reappearing. So we're quite confident that this is not some artificial signal, but actually real. So it does not depend on the data reduction method. And then we can go back and compare it, and we see that it overlaps with the spirals that we see in the scattered light. Okay, this directly raises the question, are we seeing a fragmenting spiral arm, fragmenting in the dust phase, as Cristiano showed in the theoretical talk earlier? And of course, it directly raises the question whether or not we are seeing the precursors of giant planets. So Cristiano showed you in his talk that in the dust phase, you can produce something like a planetary cores of several Earth masses. And here, if we do some typical assumptions about dust temperature and opacity, and we can convert the flux that we receive from these clumps into masses, this is like super hand wavy, because we really don't know what is the temperature here. But we can see that for something like 50 Kelvin, this would translate into several Earth masses. Okay, then finally, what happens at even larger scales? This is the sphere image, and now ALMA actually does not only give us the image that I showed you before, but it gives us a much larger field of view. So here we see the entire field of view of the ALMA observation, which goes about 10 arcseconds in both directions, and we see there are several other sources, millimeter sources, within this field of view. We have one companion to the north, we have one object to the east, and we have this thing here in the southeast. And just to give you an idea, this thing in the southeast is about 16,000 AU away from the primary. So normally we would think, okay, that's probably a background star or whatever, like how can this be related to that? But then we took a look at Muse data that normally is used for spectroscopy, but if you stack the channels, you can get an image of that. And you can see, now there's the contour of the millimeter emission that we saw before. You can see that there's actually some kind of connection between this source in the south to the outbursting star. And this, of course, raises the question directly if it is infall that we're seeing here from envelope or cloudlet in the environment. And we can also look at 13CO data. This is the moment zero map, where we see gas reservoirs around these sources in the south. And we also see this tentative connection to the primary. I say tentative because the signal to noise is not too high. Just to give you an idea, this is 10 minutes on target with ALMA. So I think this signal to noise or the confidence that we have on this data could be easily increased by spending more time integrating on this object. Okay, then. Let's go back to the continuum image. And as I told you before, we have another millimeter source that is located to the east of the outbursting star. And we also can analyze, instead of analyzing only the 13CO that I showed before, we can analyze the 12CO data. Now, the difference between, like, people who are not used to ALMA data, the difference between 12CO and 13CO is that 12CO is normally much more abundant than 13CO, which means it turns optically thick much faster than 13CO. And normally this means that we cannot look that deeply into an image of 12CO as we can into an image of 13CO. And that's what happens here. In 12CO, we cannot see the primary itself, the outbursting star, because there is some foreground material that blocks our view. And then we saw that this foreground emission is kind of centered on this eastern object. And if we look at the kinematics, so the Doppler shifted line emission of the 12CO, we see that there is some blue shifted material and some red shifted material that are cone-like, and they are centered on this eastern object. So somehow this eastern object is spilling out this material in something that it looks like a jet. And the only problem is that besides the millimeter emission, we do not trace this eastern object in any other observation. Like there's no signal in the optical, in the near or mid-infrared, which is really a question. What is the origin of this jet, and what is the physical properties of this object that we see in the millimeter? Okay, so let's to conclude, I want to just go through the images basically. We have the Muse image where we see envelope infall or some kind of capture. We have an unidentified flight object around the outbursting star. Then if we zoom in, we see spirals and an inner companion. In the sphere image, we can further zoom in the sphere image. We see a fragmenting spiral in the millimeter that gives us basically an idea of dust clumps in the system. And of course, the star or the material around the star is generating an accretion burst. Or to put it again with words to follow it, it's everything, everywhere, and at the same time. Thank you.
Thank you very much, Philippe. Maybe we can start with a question from Fernando.
Hi. So a very, very fun and cool talk. So when I was looking at this data before our continuum paper, I saw this moment one map that you showed, and there is this like red ring, and you see the outflow from the companion on the east. But my interpretation of this, and the reason I never said anything, was that what we were seeing is an outflow face on. So we are seeing like the like the red-shifted ring of the outflow, similar to what has been found by in other FUors by coincidence, of course, and that the blue-shifted side of the outflow was just maybe the environment was just too faint, and then you don't see this thing. That was like my interpretation of things. Have you tested this in somehow? Because we know that the disk is not resolved, so we don't know the inclination. We don't know where are we looking at. Have you tested this with other observations?
So you mean that the two cones that we see here, they are part of an outflow that is centered on the primary?
Yeah, so I'm saying that V960 Mon has an outflow that is face on. So this red-shifted thing is just the red-shifted cavity wall, but just enhanced.
Yeah.
That was what I thought. So have you tested this with other data that you have? I don't know.
No, because we don't have any other data of this outflow. I know that you have the apex observation, but I think there it's not really possible to resolve the.
No, in the apex thing sees the outflow from V9, where Eastern Companion sees it, but I know that that's not the outflow from the actual FUor.
We need more data, basically.
Yeah, of course. Yeah, that's always the answer. Yeah.
Robin, you get to ask one question now.
Fascinating results, Philip. I had a quick question. So your dust clump in which you constrain the mass to be 3, 4, 5 Earth mass, they're at 1,000 AU. Do you get any gas information of those clumps to see whether they're actually bound to the central star?
No, like this is one of the major things that we need, kinematics that are good enough to figure out whether this structure that we see in scattered light is actually a disk. So if we can find Keplerian rotation, or whether it is part of an infall, like you showed it yourself. If you capture a cloudlet and it falls in, it will automatically generate some spirals. And yeah, we don't know if this is like a GI disk instability or whether it is part of the infalling material. And yeah, that's definitely something that we are super interested in to get the kinematics around this area to see if it's a Keplerian disk or not.
We have time for a couple more questions.
And maybe that also goes for Lynn and Alvaro. How sure are we that this is a low mass protostar?
We constrain the mass to be 0.6 solar masses with small errors.
There was another question in the back first.
By the way, it's also very phased on. Our inclination was about 15 degrees, so in good agreement with the ALMA, roughly the ALMA error bars.
Question in the back first, and then Lynn, you had a question as well? Okay.
Hi, Philip. Great talk. So if I understood correctly, you saw a feature in 13CO which was connecting to the millimeter source in the bottom, and a feature in continuum which connected to the source on the left. So like these features are visible just in one tracer and not the other. Does that suggest they have different composition and different origin, therefore?
Yes, so I was also wondering about that, like how can it be that this one thing, like this jet is so present in 12CO and not at all in 13CO, while the sudden object, for example, it is really present in the moment zero map of 13CO, but in the moment zero map of 12CO, it's not that there is foreground stuff there. It's just it's not present at all. So I don't have the answer to why this occurs. Would be interesting to discuss.
Thanks. So thank you very much, Philippe, again. We have a last contributed talk before the coffee break. Felipe